Hey everyone, in this video, we'll be implementing a distributed task scheduler. I recently started writing a Substack, and in the last newsletter post, I discussed how you can design a distributed task scheduler. In this video, we'll be going over the implementation details. I highly recommend that you go through the newsletter post before you watch this video so you can better understand what we are doing here. The task scheduler that we designed consisted of a few components. It consisted of a scheduler that received task scheduling requests from the user and persisted them into a database. We then had a coordinator that would constantly keep scanning the database to look for new tasks that needed to be executed at the current time. If it found any tasks, it would pass them off to the workers that are registered with it. These workers use heartbeats to register with the coordinator and communicate their liveness. In case any of the worker nodes went down, the coordinator would automatically remove them from the worker pool. Once the workers were done executing the tasks, they communicate the status back to the coordinator. It's going to be a lot of fun to implement the system, so let's get on with it. So here we are inside VS Code. We won't be writing the code line by line from scratch. Instead, I've already written the code and we'll try to understand what it's doing. It's much more similar to how you'll see a code base in real life. You'll probably have some code already written, and you'll probably want to understand what's happening there. First of all, let's start from the component that probably most of our components depend upon, which is the database. In our example, and in this implementation, we are talking about Postgres. We'll be using the Postgres Docker image to set up our database. We'll use a database initialization script, which the Postgres image will pick up and will initialize using that script. So here is the Postgres Docker file. You can see that we pulled the official Postgres image from Docker Hub. We set up a working directory. And finally, we copy our initialization script to the Docker entry point folder inside the container. I've added a comment here that the Postgres image runs all the .sql, sql.gz or the script files that are found inside the entry point folder upon initialization if the data directory is empty. The data directory that we are talking about here is this directory, which is being used as the Docker volume. So this means that across restarts of our cluster, we'll still retain the data that we have. So let's see what's happening here. Inside this folder, we'll navigate into the SQL file and we'll see what we have here. We see that we have two main statements here. One is a create table statement and the other is a create index statement. The first statement creates a tasks table for us to store all the tasks that user schedules. The second statement is to create an index on this table. The table that we create is similar to the one we discussed in the newsletter. We have an ID column that is generated as a UUID by the database itself automatically. The second column is a command that the user wants to execute at the scheduled time. Third is the scheduled at time, which is a timestamp and it cannot be null. The rest of them are the timestamp phases, which are populated as soon as each phase is completed. Whenever a task is picked for execution, the picked at field is populated. When a worker starts executing the task, it populates the started at timestamp. When it completes a task, the completed at timestamp is populated, and if the task fails, the failed at timestamp is populated. Why we keep track of all these timestamps is explained in a lot more detail inside the newsletter. Finally, we create an index on the scheduled at column, since this is the column that the coordinator will later use to pick the tasks that are scheduled to run at a current time. So going back to the Postgres Docker file, we see that we pull the Postgres image and we populate the entry point folder so that our database can be initialized. And we don't need to do anything else. We do need to pass in a few environment variables which are already initialized inside the Docker Compose file. To see those, we can go to the Docker Compose YAML file. Inside the Postgres service, you can see the environment variables that we are initializing. We send the Postgres DB, the Postgres user, and the Postgres password here. These are environment variables that are coming from our .env file. The .env file is available here. For this, we're mostly using the default Postgres user and passwords, which are Postgres and Postgres, and we name the Postgres DB as scheduler. So what we're doing in the Docker Compose file is we're sending the context, which is this entire directory, as the context of the Docker file. The Docker file being used is the Postgres Docker file that we just looked at. We're sending these environment variables that we are picking from the .env file. We have a volume, which is the ./data folder, which we see right here, which we have also hidden from the git ignore so that we don't commit it. And finally, we expose the 5432 port externally. Externally exposing this port allows our other services to access it. And that's all there is to our database service, which is a Postgres database. Let's move on to the scheduler, which is the first part of the system, which we should discuss since that's the entry point for our task and is the service that a user will interact with. Let's navigate to package, scheduler, scheduler.go. This is the file that defines our scheduler server and some utility classes. The first thing that we see is a struct called command request. It has two fields, command and scheduled at. They represent a task request that the user sends to our HTTP server that runs inside the scheduler. The command is the command that the user wants to run, and the scheduled at is the time that the user wants to schedule the task to execute at. The user enters the task in the ISO 8601 format, mainly because it's easier to read and write by hand in case you're testing your program in Postman or some other API testing service. The second struct we see is the task struct. This is a struct that we use to interact with the database. It closely resembles the database model for our task table. As you can see, it has an ID field, a command field, and all the timestamp fields that we already discussed. Then we have our scheduler server. We have a port which defines on which port our server will be running. Then we have a DB connection string. This is the string that we use to connect to our Postgres database that we just talked about. Then we have a DB pool. You can see that this comes from the pgxpool library. Pgxpool is a Postgres library that allows you to set up a connection pool with your Postgres database. The reason for using a pool here is that we get a lot of benefits from shared connections. We don't have to set up new connections whenever a new request comes our way. We have a pool of connections and we utilize one of them. The library itself dynamically manages the number of connections it's holding, how it manages the load across these connections, and also the resource cleanup. Then we have our context object. We use it to manage our goroutines as well as other asynchronous processes in our system, such as the database connection pool. Then we have a cancel function, which is sort of related to the context. Whenever you call the cancel function, your context receives a done signal. And whenever that happens, we can capture that signal and then do whatever we want to do. For example, terminating a goroutine or something like that. Finally, we have the actual HTTP server object, which comes from the built-in HTTP package. We see that there is a function called new server, which simply creates a new server instance of the scheduler server. It takes in the port at which the server should be running, as well as a DB connection string that it should use to connect to the database. Note that this just creates the scheduler server object. It does not start any of those services. That is the job of the start function, which is a function for the scheduler server struct. What we see here is that first thing that we do is connect to the database and set up our database pool. We use one of the utility methods that we define inside the common package. Let's see what that does. What we see here is a simple implementation with the retry mechanism to connect to our database. We simply try to connect to the database using the pgxpool connect method. In case there is an issue, we retry this for 5 times with a sleep interval of 5 seconds. The reason we've added this retry is that whenever we are setting up our cluster, there's a chance that it takes a little bit of time for the database to come up. In that case, we shouldn't immediately fail in case we're not able to connect to it. Therefore, we allow 5 retries to connect to the database before sending out an error message. You could use a more sophisticated approach here, such as exponential backoff, but this is just a demo project. Therefore, a simple 5-second sleep should be enough. Let's go back. So once you've connected to the database, you register handlers with your different HTTP routes, which are schedule and status routes. The schedule route will be used to schedule new task requests, while the status route will be used to get the status of already scheduled task. We then set up the HTTP server and finally run the HTTP server in a new goroutine so that it can run asynchronously while we await the server shutdown. The server shutdown function is quite simple. The await shutdown method waits for an interrupt or a SIGTERM signal on the signal channel that we make using the os.signal package. Then it blocks until it receives an interrupt or a SIGTERM signal on this channel that we just created. And once it receives one of those signals, it returns. Going back, let's discuss how we're doing the handling of our schedule and status endpoints. Let's jump into the handle schedule task method of our scheduler server. We see that the first thing we do is we simply run a validation to make sure that the user has sent us a post request on this route. Then we take the JSON body from this request and decode it into our command request struct. We receive the time in the ISO 8601 format, and therefore we parse it into the Unix timestamp, since that's what we store inside the database. Now that we have parsed all the information that the user has sent us, we generate a task object and we send it to the insert task into DB method inside our scheduler server. This method inserts this task into the database and returns a task ID that was generated by Postgres using a UUID. Now that we have the task ID, we generate a response and we send this response back to the user. And that's all there is to the handle scheduled task method. Let's get back. The status endpoint handler is also quite simple. Let's jump into this method and see how it works. We first run a simple validation to ensure that the user is sending GET request on this route. Then we read the task ID from the query parameter. We run some simple validations to ensure that this query parameter is present. And finally, with this task ID in hand, we query the database using a database pool to get all the information that we have about the task that the user is requesting. We send back all of the information that we have in the database in the form of a JSON response. We build the response with a couple of if statements to ensure that we are not sending any invalid or null values. Once that's done, we write back the response to the user. And that's mostly how the scheduler works. And now we're ready to move on to the next component of our system, which is the coordinator. For that, let's head over to package, coordinator, coordinator.go. The coordinator and the workers make use of gRPC for communication instead of HTTP. There are a couple of reasons for why we want gRPC instead of HTTP for such inter-process communication. gRPC is much more low latency and high throughput compared to your regular HTTP since it uses protocol buffers for serialization. Protobufs are much more efficient and faster than sending JSON responses. Moreover, it uses HTTP 2 right out of the box. This reduces the latency and improves the speed of communication because of smaller header sizes and multiplexing. gRPC also supports strongly typed contracts, which means that the gRPC services that we define in our protobuf file defines a strong contract between the client and the server, which reduces the likelihood of miscommunication in case of contract changes over time. Since both the coordinator and the worker make use of gRPC to communicate with each other, it makes sense to understand the gRPC contracts that we are going to implement in both the services before we dive into the code. To check out the gRPC services, head over to package, gRPC API, api.proto. This file defines a couple of things. The first being the task status enum. This enum defines the status of a given task. This can be queued, started, complete, or failed. We then define the worker service. This service is implemented by all our worker nodes. It defines only a single RPC, which is the submit task RPC. The coordinator uses this RPC to send tasks for execution to the workers that are registered with it. We then have the message definitions for the task request as well as the task response. They are quite simple. The task request simply contains the ID of the task we want to execute as well as the command. The command is stored as the data. Then we have the coordinator service. This contains one RPC called submit task. We don't need to worry about this. I just added this for some testing purposes while I was developing this system. This is followed by the send heartbeat RPC. This RPC is quite important since the workers use this RPC to register themselves with the coordinator, and then the coordinator uses this RPC to subsequently keep track of all the workers that are alive. In case one of the workers does not send heartbeats for a given time, the coordinator removes that worker from the worker pool. In case the worker recovers later, it can start sending heartbeats again, and the coordinator will automatically register that worker in its worker pool again. This is followed by the update task status RPC. The workers use this RPC to update the status of the tasks that they are executing. This is followed by the request and response definitions for all these RPCs. They are quite simple for the most part. What we'd want to look at is the heartbeat request. This includes the worker ID as well as the network address of that worker, which wants to register itself. Now that we've looked at the protobuf definition, we are ready to go back to the coordinator code. But before that, you might be wondering, since this is a protobuf file, how do we access it inside Go? For this, we make use of the generated files from this protobuf. gRPC provides you tooling to generate code for whatever language you want to target in your gRPC code. I have the script to generate the Go code for this protobuf, and that generates these two protobuf files. You don't need to edit them, nor do you need to commit them to Git, since these will be generated every time you want to build your Docker images. Now we can go back to the coordinator code. The first thing we see here is the coordinator server struct. The first field in this struct is an unimplemented coordinator service server. This comes from the generated file from our gRPC service. We add this here to indicate that our coordinator server implements the coordinator service interface from the gRPC API. If you hover over it, you can see that it includes all the RPCs that were defined in the API.proto, and we'll need to implement these in our Go code. This is followed by the server port. This is the server port at which our gRPC server will run. Then we have the listener for our gRPC server, the gRPC server object itself. Then we have a map, which is a worker pool. This map is keyed by the worker ID and contains the worker info. The worker info includes the number of heartbeat misses a worker has had, the address of the worker, the gRPC connection object, as well as a client to talk with this worker. We maintain one separate client for each worker that is registered with us. Moving on, we have the worker pool mutex. We use this mutex to lock the worker pool whenever we access it. This is followed by a helper data structure called worker pool keys, which helps optimize our round-robin algorithm by helping us choose the next worker server to send our tasks to. Since multiple goroutines might be accessing this, we have a mutex over this as well. This is followed by the max heartbeat misses we want to allow for a worker before it gets deregistered. We then define the heartbeat interval. This is the interval at which each worker should send its heartbeat. Then we have the round-robin index. This is a helper member which defines which worker is next in line for the round robin in our worker pool. We then have the DB connection string which we use to connect to Postgres. We have a DB pool to connect to Postgres. We have a context and a cancel object which serve similar functions as they do in the scheduler. And finally, we have a wait group to manage our goroutines. Moving forward, we see that we have a new server function which instantiates our coordinator server. Then we have a start function which starts our coordinator server. The start function is a little bit complicated and will take some time to understand what it's doing. The first thing it does is it launches the manage worker pool function in a goroutine. We'll see what this function does in detail in a bit, but as a high-level overview, this goroutine is responsible for keeping track of which workers are still active and which workers need to be removed from the worker pool. Next, we start the gRPC server, followed by connecting to the database using our database pool. Then we launch another goroutine, and this goroutine scans the database for any tasks that need to be executed in the next 30 seconds. It keeps firing queries on the database to check which tasks need to be executed. We make use of some clever SQL in this method, and we'll go over it in a bit. Finally, we return an await shutdown method which blocks until we shut down the server. This is very similar to what was happening in the scheduler server. Before we try to see how the manage worker pool method is working, it's better if we understand how the send heartbeat RPC works and how different workers register with the coordinator and how the coordinator uses these RPCs to keep track of active workers. Then it would make more sense to see how we are deregistering workers which seem to be inactive. So let's head over to the send heartbeat method which we implement from the coordinator service interface. So we see that the send heartbeat method takes in a context and a heartbeat request, and it returns a heartbeat response or an error. As soon as we enter this, we take up a lock on the worker pool mutex. The reason for this is we do one of two things when we receive a heartbeat. Either if this is the first heartbeat that the worker is sending us, we register it, which requires us to make changes to our worker pool. Or if this worker is already registered, we reset the number of heartbeat misses that it has had. So once we've taken the lock on the worker pool mutex, we get the worker ID from the heartbeat request. After that, we check if this worker already exists in our worker pool. If it does, it means we have already registered this worker and we reset its heartbeat misses. Otherwise, we register this worker into our worker pool. To do that, we first set up a connection with this worker. We use the gRPC dial method for the same. Once that is done, we save the worker details inside our worker pool using the worker info object. We save the address, which is the network address, the gRPC connection we just created, and also a client to communicate with this worker. Once we've added the worker into our worker pool, we take a lock on the worker pool keys mutex. This is the mutex that guards the worker pool keys data structure. Worker pool keys is nothing but a list of integers, and the integers being the worker IDs. We make use of this data structure to help us select the next worker that we want to send the tasks to in our round robin scheduling. We can't do that directly over the worker pool since the keys in a map do not have a definite order. Therefore, we save those keys inside this array. And as you can see, we need to regenerate this array every time a new worker registers with us. But that's alright, since we don't expect that new workers will be registering every other second. Once that's done, we print the registered worker message and finally return a heartbeat response. Now that we know how the worker registration and heartbeat works, we can go ahead and understand how the manage worker pool method operates. So we first head back to the start method. From here, we go into the manage worker pool method, which we launch into a separate goroutine. The first thing we do in this method is we add an entry into the wait group. Adding an entry into the wait group allows us to gracefully wait for this goroutine to end when we are shutting down the server. Next, we set up a new ticker. The ticker ticks every time we want to check for inactive workers. This duration is calculated by the maximum number of heartbeat misses we want to allow multiplied by the heartbeat interval. We defer the ticker to stop so that it stops once we return from this function when we are returning from this goroutine. We use a for select statement to concurrently wait for signals on either the ticker or the context. We receive a done signal on the context when we shut down the server and call the cancel function that we discussed earlier. Every time the ticker ticks, we call the remove inactive workers method. Let's see how that works. Inside this method, we again take a lock on the worker pool mutex. We take a lock since it's possible that we will be removing some workers from the worker pool and hence we'll need to make some changes. We iterate through the worker pool and check for the heartbeat misses for each worker that is there. In case any of the heartbeat misses is greater than the max heartbeat misses we allow, we close the gRPC connection with that worker. We delete its entry from the worker pool. Then we regenerate the worker pool keys data structure and finally return. Otherwise, if it's not yet at the max heartbeat misses that it's allowed, we just increase the heartbeat miss count. And that's how this method works. So let's go back to the start method. We can now begin discussing the scan database method, which we also launch in a separate goroutine. This method is probably the most interesting one on the coordinator. We see that we first set up a ticker to tick at every scan interval. In our example, we have the scan interval set to 10 seconds. We then defer the ticker to stop once we return from this goroutine. Next, we have a for select loop, which has two cases that it waits upon. It waits for signal on two of our channels, the first being the ticker, which ticks at every scan interval, and at every scan interval, it runs the execute all scheduled tasks method in a separate goroutine. And the second one is the context done channel, which receives a signal whenever the cancel function for this context is called, which happens when we are shutting down the server. Now let's focus on how the execute all scheduled tasks method works. First, we set up a context with a timeout of 30 seconds and store its cancel function and defer its execution to the end of this function. Next, we begin a transaction on our database. This transaction will contain the statements to select and update our tasks table. Before we get to that, we set up some cleanup functions. We defer a rollback in case of an error so that the transaction can be closed if we do not complete it successfully. Next, we run a select query on our database. Let's see what it does. Select the ID and the command from the tasks table where the scheduled at time is within the next 30 seconds or before that. And we also make sure that the picked at column is null, so we do not pick tasks that have already been picked by the coordinator. Finally, we have the for update skip logged clause. The reason for this clause is explained well in detail in the newsletter post, so I again highly recommend that you go through that to understand why we are doing this. Once we've executed the query, we start reading the rows that were returned. We scan the ID and the command from each of these rows and append it into the tasks array. Next, we send each task in the tasks array to the submit task to worker method, which is responsible for sending this task to one of the workers that are registered with the coordinator. If we are able to successfully submit the task, we update the status of the task by updating its picked at column and we set that column to the current time. Once we've submitted or gone through all the tasks, we finally commit the transaction so that the changes are persisted and are visible to the other transactions. And finally, let's take a look at the submit task to worker method to see what that does. So let's jump into this method. The first thing we see is we get a worker ID from the get next worker method. What this method does is it takes a lock on the worker pool keys mutex, because now what we are going to do is we're going to get the next worker from the worker pool keys. We get the worker ID from the keys data structure and we use that worker ID to get the worker info from the worker pool. Then we increase the round robin index so that the next worker in this data structure can be selected the next time someone calls the getNextWorker method. And finally, we return this worker's info to the caller. We just have a sanity check that some work was returned. And finally, we use this worker's worker service client to submit the task before returning any error that might have been returned. And this error could be nil in case of a successful submission. With that, we complete all the logic inside the coordinator and we are finally ready to move on to the last component of our distributed system, which is the worker. So head over to package, worker, worker.go. The first thing we see here is the worker server. It's quite similar to the coordinator server in a couple of ways. Similar to the coordinator, it implements a service interface for the service that it implements. For the worker server, we implement the worker service server. It contains the RPCs that we need to support, which in this case is the submit task RPC. Then we have a worker ID, the port on which it runs its gRPC server, the address of the coordinator that it needs to register with, the listener for the gRPC server, the gRPC server itself, an object to maintain the coordinator connection, a client to talk to the coordinator using gRPC, a variable that stores the heartbeat interval, a task queue to store the task requests that come its way, a simple map of tasks that it has received just for bookkeeping purposes, a mutex for the same, and finally, a context, cancel, and a wait group. The context and cancel functions serve the same purpose they used to in the coordinator, which is to manage the cleanup of goroutines, and the wait group is used to manage the worker threads in the worker pool that we have. These worker threads are responsible for picking up tasks from the task queue when they are free and when they are done with processing the previous tasks. So let's go forward. We again have a new server function, which is very similar to the other new server functions we've seen so far. It instantiates a worker server, but it doesn't start it. To do that, we go on to the start method. The first thing it does, it starts a worker pool, then it connects to the coordinator, then it starts another goroutine to send periodic heartbeats to the coordinator. It then starts the gRPC server and finally blocks on a wait shutdown. The connect to coordinator function is trivial. It simply dials a gRPC connection and sets up a service client. What we are interested in here is the worker pool and the periodic heartbeat methods. Let's go to the worker pool method to see how it works. It takes in an argument which is the worker pool size. This defines the number of threads you want to run inside our worker pool inside this worker node. So we go into this worker pool. What we see here is a for loop which runs num worker times, and each time it runs, it adds an entry into the wait group to mark that it has one goroutine that it has launched for one worker. And then it launches a new goroutine with the worker method. What the worker method does is quite simple. It launches the for select loop. This loop waits on the task queue for new tasks from the coordinator, and whenever it is done processing the task, it updates the status for the same. It also listens to the done channel on the context in case we've called the cancel function to shut down this worker. The update task status method is quite simple. All it does is send an RPC on the update tasks RPC method of the coordinator. The process task method also does not do much. Since this is a demo, we are not really processing any tasks. All we are doing is sleeping for some time to simulate as if we are processing some task and to add an artificial delay. So going back to the start method, we see the last thing that we need to discuss is the periodic heartbeat method. And it's quite simple. All it does is add an entry into the wait group, set up a new ticker with the heartbeat interval, and finally launch a for select loop which waits for ticks on the ticker channel. And every time the ticker ticks, we send a heartbeat to the coordinator. The send heartbeat method is also pretty simple to understand. We get the worker address, we get the network address as well as the port number, and then send this along with the worker ID to the coordinator. And that's all there is to creating the worker for our distributed system. So the last thing we need to see is how we launch all of these different services and see our distributed system in action. The launch scripts for each of these services are present inside the command package. So head over to command coordinator main.go to see how the coordinator service is launched. It's quite a small script. All it does is it reads a flag to get the coordinator port on which it should run, which defaults to 8080. Then it gets the DB connection string using a utility function inside the common package. All this function does is it reads a few environment variables and generates a Postgres connection string, and it returns it to the caller. Once we have that, we pass it down to the new server function in the coordinator package to get a coordinator server, and then we start the server. A very similar thing happens in the other packages as well. For the scheduler, we do a similar thing as well as for the worker. So let's see how we've set this up inside Docker Compose, which lets us test this distributed system quite easily. So closing all these files, we go into the Docker Compose YAML. We define a couple of services here. We already went through the Postgres service. Similarly, we've also defined the scheduler service, the coordinator, as well as the worker. We define the environment variables you want to supply. These include the Postgres credentials, the ports you want to expose, and the dependent services. So you can see the scheduler and the coordinator both depend on the Postgres service, and the worker itself depends on the coordinator. This ensures that all these services are launched in order. You can go to the Docker files for each of these services to see how they are set up. They're quite simple. Most of them just install a few dependencies, copy the required files, and finally launch the binary that we've built from our main.go inside the command package. And now it's time to launch this entire distributed system using Docker Compose. So we'll open up the terminal and we have this Docker Compose command to launch this. You can run Docker Compose up with the build flag if you want to build this entire thing from source, or in case you've already built it, you don't need to have this flag here, along with the scale tag to define the number of worker services you want to launch. In my case, I'll be launching 3 workers. So press enter to run this distributed system. In case you're running this for the first time, it will build all the Docker images, so it might take a little while. In my case, you can see the logs from the different services. In case of the Postgres service, you see that the log says that there's already a database that already exists, since I have this data directory here, which contains my Postgres files. After that, you can see that your workers connect to the coordinator and they connect to the coordinator successfully. And once they've done that and they've sent the first heartbeat, the coordinator registers all of these workers. The last thing we need to do is to send a testing scheduling request. So let's open Postman to do that. So we're inside Postman and we can see that we have a sample request ready here. We are making a post request to the scheduler on the schedule endpoint. We have a JSON body with the command and a scheduled at timestamp. The scheduled at timestamp is present in the ISO 8601 format, which allows us to define the time on which we want to schedule this. This is today's date as well as the current time, or at least close to the current time. So when we send this request, we should be able to schedule a task on our distributed system. So we send the request and we receive a task ID generated by our Postgres database. Now we can use this task ID to query the status of this task. But before we do that, let's check out the logs on our distributed system. So we see that we received a schedule request, and this is logged by the scheduler. It prints the command as well as the time that we've sent from Postman. Since the scheduled time was close to the current time, it was immediately picked up by the worker. It processed the task and finally updated the task status inside the Postgres database. To check the status, we can go and check the get status endpoint here, and we can copy the task ID that we received when we made the scheduling request. We can go to the get status tab, we can paste the task ID here, and we can send this request. And here you see you have all of your execution phase timestamps. Therefore, we can verify that our distributed system is working as expected. In case you want to dig deeper, we also have some integration tests set up here, and you can run through those to see how each component of the system works and how we are testing each of these different services. And that's it for this video. I hope you enjoyed it and learned something new. So go ahead and subscribe to my Substack for some more interesting content on software and computer science, and I'll see you in the next video.